Section 1.2 Line Segments and Congruence. These concepts are going to be really fairly simple. For instance, postulate number one. Remember a postulate? Well, you don't have to remember it, I guess. We just talked about it once before. As long as your short-term memory is working, it's not a problem. Postulates, axioms, and undefined terms. These are all things we accept. Much like Ben Franklin, we hold these truths to be self-evident. Our first self-evident truth is the ruler postulate. And the ruler postulate basically says, I'm sorry I'm chuckling, but if you're not, ooh, that's not a very good line. Hold on. There, that looks a lot better. Now, say we have a line here. Guess what postulate number one says? It says we can measure that line. Well, pardon me. Line segment, of course. I did it again. All year I'm going to end up correcting myself, saying, I mean line segment, even though I just said line, because my mouth is lazy and just doesn't want to get into that second word. A line segment has measure. In other words, it's a measurable quantity. It might not sound like much, but throughout geometry we're going to find things that can be measured and things that can't be measured. For instance, over here we have array. Remember, we learned about those. This goes off to infinity. Well, can't measure that. We have a line down here. This goes off to infinity in both directions. Well, can't measure that either. The segment, yes. Got a spot here and a spot here. And postulate 1 says it is in fact possible to measure the distance between this and this. That might seem kind of obvious, but in mathematics there's no such thing. As a matter of fact, you may not have heard of it yet, but frequently in probability and maybe other applications, you'll hear somebody say something like, we have a set of elements and then we choose one. Well, people were saying that for a long time before some guy stood up and said, wait a minute, how do you know you can choose one? Which sounds like a ridiculous question, until he said, look, we've got rules for absolutely everything. We've got axioms that say we can do this. We've got postulates. We've got theorems that put everything together. I don't see any rule or postulate or definition anywhere that says, given a set of elements, we can choose one. Turned out he was right, so they had to actually write something called the axiom of choice, which says, given a group of elements, you can choose one. It's allowed. Don't take my word for it. Google it, search it on Bing, whatever you want. Check out axiom of choice. It's an historical fact. It's there. So postulate 1 is along those lines for most rational people. Yes, indeed. Given a line segment, you can, in fact, measure it. Was there anybody in the room who didn't think we could? Now, the second one, the segment addition postulate. This one is along fairly obvious grounds too, but we have to actually state it. That way when we use it later on, we can say that we're not breaking any rules. We can point to postulate number 2 and say, I know this is true because postulate number 2 says so. That's pretty much what they're there for. And what it says is, if we break this line up here, the distance, which we have already from postulate 1 decided exists, this whole distance here, whatever it is, call it L, is the sum of, and let's use some subscripts here, you might as well get used to them. A lot of books say you should call this L sub 1. Yeah, I guess you could. I'm just going to always say L1 and L2. Let's say that L2 is the distance from there to there, and there to there, and L1, distance from there to there. You've probably seen that notation before. These arrows are designed to indicate the This number in the middle is the length from here to here, and this number in the middle is the length from here to here. Of course, you've probably seen them written and drawn much better than this. I'm not going to win any awards for my handwriting. And what the second postulate says is, now, get a good grip on your seat. I don't want anyone of you to fall over when we write this down. L equals L1 plus, what do you think? L2. Yes, indeed. Our second postulate, our segment addition postulate, says that if a line is broken up into two pieces or any number of segments, the sum of the lengths of all those segments is equal to the total length. I bet most of you would have guessed that anyway, so I don't expect you're going to have a hard time remembering this postulate. Usually the hard part is remembering to cite it. You'll be inclined to just automatically do it and not list the reason for doing it. That's fairly common. I don't mean that in mathematics it's common to not list the reason. I mean it's a common mistake. Pardon me. So there's our two big facts for this lesson. Number one, if you have a line segment, you can measure it. There's such a thing as a distance from here to here. And if you break that up into sections or segments, these segments will add up to the whole. Or in other words, the parts, when added together, will equal the whole. It may sound obvious, that's not always true. I mean, when you go home, chop up your dog into 4 legs, 1 head, and a body. You put it back together, you find that the parts don't equal the whole. You don't have a dog anymore. But in the case of mathematics, if you chop up a line into as many parts as you like, the parts together will equal the whole. So let's do some exercises. Let's prove how simple this really is. Let's start with a couple of real simple ones. I bet you can do most of these in your head. We know that this exists. Of course, they give it to us. XZ here, and this is the line XZ. Line segment XZ. When you're talking about the measure of something, we usually just write XZ, and then we write equals 30. That's the length of XZ. In other words, we could put length in front of here. If I wrote XZ like this, that means the line segment XZ. It doesn't actually refer to the length of XZ. XZ. What's the length of XY? Well, I think the segment addition postulate tells us that segment XY, that is the length of a segment XY plus the length of the segment YZ equals X, length of XZ. So it would follow that XY equals XZ minus YZ. You see, we just moved it over there and turned that into minus YZ and got it out of there. I assume you followed that real quick. Now, what is XZ? Well, just like it says up there, it's 30. And down here, well, YZ is 7. So we get 23 for XY. Right. Like I said, you probably did that real fast. Same thing up here. We've got AC. They give us the whole thing. That's 42. AB. That's 27. And BC. Well, just like up there. 42 minus 27. Again, from the segment addition postulate. And that looks like, let's see here, 5, 1, 15. I hope so. Here's another good one. And as I try to mention in every video, these are taken from McDougall Little geometry. And this is good. It's good because it's a common mistake. I think I've probably done it, and I've seen students do it over and over and over. It's an easy kind of simple little mistake to make. And it's cool that they created a problem out of it to help you avoid doing things like this on a standardized test or any other test. And the figure at the right, AC equals 14, AB equals 9. So somebody decided, and this happens a lot, to treat it as if AB was 9 and AC was 14, and add them together and say that as if they were looking for the total. And that's not what's being asked for, is it? They're asking for this little piece here. So if AB is 9 and the whole thing is 27 from here to here, then what you really have to do, obviously, is subtract the 9 from the 27. That should give you something close to 18. But remember this. It's good to learn from your mistakes. It's better to learn from other people's mistakes. Now this little problem here, what we have is a list of points. After we plot these points, we're going to take a look at the line segments created by them and determine whether they're congruent or not. So what the heck is congruence? Well, I held that back from you until we got to a problem on it. We already know about equality in numbers. For instance, 1 over 2 equals 2 over 4. Well, no problem with that. Or 6 equals 2 times 3. These equalities we use all the time and they make sense to us. But suppose I draw, oh boy, this is going to be interesting. Let's see if I can do it. One line, and then I draw another line exactly the same length. They don't have to be parallel. It's easier for me to see if they're the same and easier for you. And I call this line AB, because I'll just draw in 2 points here, B and A, and I'll call this line XY. Now, it was my intention to draw both of these with exactly the same length. So I could write AB, meaning the length of AB, equals XY. Or I could write the line segment AB is not quite equal. A little squiggly over the equals. That means congruence. And that's what you say, I think in a previous video I mentioned that 2 chairs could be identical, but they couldn't be equal. Equality is kind of an abstract concept, where congruence is a little more concrete, really. If you're talking about, well, in a sense, actual objects, not always, after all. Some of the constructions in geometry are a little abstract too. But take the pyramids, for instance. If 2 pyramids were exactly the same, they couldn't be called equal. Not in geometry. They would be called congruent pyramids. And that's all there is to congruence. It's not a big deal. If you understand equality, well, just remember that it's the kind of equality you use when you're talking about objects, when mathematically it isn't correct to say equal. If you remember that, you pretty much got it figured out. So, let's take a look at these. First thing we have to do is plot these. In order to do that, I think we're going to need some kind of a grid on which to plot points. Ooh, and there's a grid now. So let's get to work. J is minus 6, 8. And remember from Algebra 1 what that means. That means x, as always the first one, x is 6, and y is minus 8. So for our first point, we've got minus 6 for x, and minus 8. Well, there's minus 4. There's minus 5. Whoa. Now I'm going to have to estimate this a bit, aren't I? 5, 6, 7, 8. Right about there. I think I should have picked an easier one for myself. We'll see what happens. Minus 6, 2. Well, there's minus 6 and there's plus 2. What about L? Minus 2, minus 4. Minus 2, minus 4. These would look a lot better if I labeled them, wouldn't they? See, that's the problem with the video. If we were in class, you could have screamed at me a minute ago. And this is J down here. We got one more point to plot. M, minus 6, minus 4, way down here. And now, JK, well, jeepers. I really need to remember to label these things. Okay, that's point M. Now let's produce line JK. So we want line JK and LM, and then we want to see if they are congruent. Well, even estimating that minus 8 way down here, I could have been quite a bit off, and I can still safely say that J and K and L and M are absolutely not congruent. Look at the difference in size there. And if we make any mistakes, well, let's see here. We've got minus 6 for an x-coordinate for K, that's right. And minus 6 for an x-coordinate for M, that's right. And for M, we also have minus 6. So that's K, J, and M all have minus 6. And that's why we have set up like this, where you can see that actually M lies on JK. And it makes sense that it would, because x-coordinates are the same for 3 of the 4 points. And let's make a quick review of algebra here. You already know how to do this, of course. I'll just remind you. How do you find the distance between J and K? Well, you could count, but let's suppose that it was actually bigger, and you didn't have time to count them all. How would you do that? Well, you subtract the smaller one from the bigger one. Or, actually, in terms of distances, it doesn't matter, because distance is always an absolute value, which you probably learned in Algebra 1 also. In this case, say we want the distance from J to K. Well, we have minus 3 here, minus a minus 6. And that, of course, is minus 3 plus 6, which equals 3. Very simple. What about from K to M? Well, same thing. 6 minus a minus 3. Why am I bothering to go through all this when you certainly know how to do it? Oops. I hope you don't know how to do that, because that would be way wrong. Let's try that. Okay. And that equals 9. The reason I bring it up is because you would be amazed how many people are going to compute the distance, say, and that was, remember, with the line over it, that's the segment. If we just write km, that's the length of km. How many people would just, without thinking, write 6 minus 3 and decide the length was 3? Obviously, if you did that, you were in a hurry and didn't bother to look back up here and could probably visually inspect it. That's not a very accurate looking answer, but it happens all the time. It's very easy to get these negative things all confused. You end up adding or subtracting negative numbers when you should be doing the reverse of that. Pay very close attention to negative numbers. Remember, when you're subtracting a negative number, you're really adding. And when you're adding a negative number, you're really subtracting. I tell you, those two little facts right there will get you through most of it. And yet, you'd be amazed how often, and you might do it yourself, without thinking about it, you'll do something like 6 minus a minus 3 and come up with 3. And it'll make you look real bad in standardized tests. So don't do it. Okay, here's an interesting question. According to this diagram here, is it possible to use the segment addition postulate to show that FB is greater than CB? Well, let's start with that one. Let's see here, what is FB? We can see this goes from here to here. Is it possible to show that that's greater than CB? Well, I would say it is. And I would say it this way. The segment addition postulate says that FB equals FC plus CB. Now, the question is, since FB equals FC plus CB, is FC plus CB greater than CB? So long as FC is not equal to 0, it is in fact greater. And if you wanted to include the fact, or the possibility that FC equals 0, then you could write greater than or equal to, and you'd have yourself a theorem that would always be true. Or you can simply say that as long as FC is not 0, this part right here is always going to be true. Remember, we're talking about lengths, not just any old number. So, we already know that none of these numbers could ever be negative. In other words, we absolutely will never have the situation such as that. It could be equal to 0, in which case it's just a point, not even a line segment, really. But this is out. That can't happen. Forget that part. It could never be less than 0. It might be equal. Bring these 2 points together and keep getting them closer and closer. Boom, 0. But it's never negative. And that helps a lot with this particular equation here. Okay, so much for that. What about this one here? Okay, I've drawn AC and DB, shaded them in different color. And now, when we look at this, we can ask ourselves, is there a way to use the segment addition postulate to show that AC is greater than DB? Well, what the segment addition postulate tells us is that AC is equal to AD plus DF plus FC. It also tells us that DB, this one here, is equal to DF plus FC plus CB. So now we can start comparing and say some of the terms in both of these are equal. For instance, DF and DF, they both contribute here equally, so just cross them out. And it's the same thing with FC here and FC here. They're part of both of them, so we get rid of those. The question is AC bigger than DB? Which is the same as saying, is AD bigger than CB? Well, is there anything in the segment addition postulate which tells us this segment is bigger than this segment? No. Although, if we're going to assume this is drawn to scale, even my eyeballs can see that this is smaller than this. Normally, in a standardized test, they're going to say, don't pay any attention to the visual representation, what they're going to say is the visual representation may not be accurate. This is not drawn to scale. So you can't just look at it and say AD is smaller than CB because it looks smaller. They didn't say that in this one. So this is the analysis, and this is how you could do it. And now it comes down to, is AD greater than CB? If you want to go by how it looks, then okay, I guess we use the segment addition postulate to show that it is. If you don't want to assume that this is actually drawn to scale, then the answer would be no. These are really great authors, and they do a really great job. It's my opinion, they should have stated whether the diagram was to scale or not to scale, so we could really know whether this answer was supposed to be answered that way or not. Normally, you don't assume that diagrams are to scale. You don't just go by how things look, you go by the actual numbers. And if all you have is numbers, then no, you can't say this for sure, because you can't know for sure this is drawn correctly. AD might actually be larger than CB, they just didn't draw it that way. We don't know. Okay, here's a good one. They give you some information. Obviously, you're going to use the segment addition postulate to figure this one out. They tell you that VZ, that is the entire line here, line segment, is equal to 52. And then I'll say 52 what? We're just going to assume arbitrary units. It could be 52 inches, 52 feet, 52 centimeters, 52 light years. It just doesn't matter, as long as we use the same units all the way through. Z is 20 units. And they also tell us that this segment is the same length as this segment, which is the same length as this segment. So how do we find this part here? Well, the segment addition postulate says VW plus WX plus XY plus YZ all equals, in this case, 52, because we know it equals VZ, and that is given as 52. But the segment addition postulate actually tells us more than that. It's kind of arbitrary how we break things up. For instance, we could have said that the entire line, which as we know has length 52 now, is equal to VW plus WZ, or VX plus XY plus YZ. With all these points here, there's a ton of ways we could have broken this up. What we want to do is break it up in the most useful way. What's that going to be? Well, we know that each of these is equal. So the total length from here to here is going to be, let's introduce a variable that we're not already using up here. I'm not sure what we should use. Let's say 3L. L represents any one of these lengths, right? Well, that's ZW, or let's say WZ, put it in the same order. Now what about this? Well, if L is one of these lengths, and 20 is the length over two of them, then we can also write that 2L equals 20, or L equals 10. In other words, each one of these is 10 units. So let's break this up. Oh, wait a minute. I kind of like the way we broke it up over here. look at this. If we're looking for VW, and we can figure out what that whole other side is that doesn't include VW, but is everything that doesn't include VW. So if we know this, we're done. And I think we know this. We've decided that this length here, L, is 10. And there's 3 of those, which means WZ, this part here, is 30. So what have we got? VZ equals VW. That's what we were looking for. Find the VW. That's the one crumpled up under the truck. Equals the entire thing, VZ, which is 52, minus this part here, which is 30. And what do we get? 22. You see, the segment addition postulate can be used in a whole bunch of different ways. We broke it up this way, we broke it up this way, and this one turned out to be the useful one. We could have broken up a whole bunch of other ways, but they might not have helped us much. Here's a good one. I think it's always good to go back and review the things you've learned previously, because no math class exists all by itself. History, a lot of classes you might be able to take one without worrying too much about the others, but math pretty much goes in order. And there are lots of problems in geometry which require algebra. Luckily, you've already taken algebra. So let's put it to use. Again, in a problem like this, what is the length of VG in its multiple choice? Now, it's tempting to look at it and say, well, anybody can see. Like, you might want to try to make use of the fact that EF looks like it's shorter than FG is all I'm trying to get at. Don't do that. Just treat it as if F might be over here or it might be over here. Just because the diagram shows it that way, don't ever assume that the drawing is accurate. Sometimes they tell you explicitly the drawing is not accurate. Sometimes they don't mention it. I would never assume that the drawing is accurate. That's my advice. So let's not assume the drawing is accurate. Let's pretend we don't know anything at all. How the heck are we going to do this? Well, we have the segment addition postulate once again, which says EG equals EF plus, well, come on, there we go, EF plus FG. And EG is what? Ooh, plus 1.6 times X. That's all we know right now. But what else is it? Well, it's from the segment addition postulate, we know it is 6 plus X. Now, what we have to do is solve this equation, which gives us 6 equals, I'm going to put it over here. I'm doing this a little bit backwards, but we got 6 here. Let's subtract X from each side. This is 1.6X, and this is X. We could also write that as 1 times X, so we subtract X from 1.6X, and what do we get? 0.6X. Okay. Well, suppose we divide through by 0.6. What do we get for X? And what's that going to be? Well, I'd say 10. What would you say? Which means if X were 10, we can write a 10 down here. Which one of these? Well, there we go. We got one. That's one thing nice about multiple choice. And it's a good way to check and see, if you made a mistake, because if you don't see your answer listed up there, chances are you did something wrong. Either that or you deserve a PhD. But look at what else they did. This is the kind of tricky stuff you got to watch out for on standardized tests. You solved for X, and you got 10. And you did so much work to get to this. You go, oh, cool, I'm done. I got 10. And you look up there, and, oh yeah, there's a 10. Cool. And you go, hit C. No. What you have to remember is you did all that work to get X, so you could plug it in over here, and then put it all together and get 16. This happens all the time. That's why they put it up in there. They're basically evil people who want to trick you. You're going to do all this work, and after that you're going to get the wrong answer because they put the answer for X up there, and your eyeball might just naturally just jump to it because you're going to be in a hurry, you'll be nervous. So pay close attention and don't let them do that to you. Here's a problem which demonstrates in a very basic way the segment addition postulate and how common it is and how often you would probably use it without even thinking about it, even if you've never taken geometry. For instance, right here we've got a bar graph. Suppose you hadn't even taken this class, and they said these are the number of wins, these are the losses. What's the percentage of games lost? Well, it's kind of a negative way to look at it. Usually people want to look at the games won. Okay, but in this case we're going to work out the loss percentage. Glad I'm not playing on that team. What we have here is we just add up these segments. 1, 2, 3, 4, 5, 6. And I think it is 6, and I wrote it down here. 6 wins. Over here, this bar graph, each one of these up represents a win. Losses are 5. Now, without even giving it any thought, the loss percentage is the number of losses divided by the entire number of games played, which is 11. That's equal to, you can pull out your calculator and come up with with an actual decimal number if you want. I'm not going to waste time on that part of it. You know how to do that. It's the last part here. How are you applying segment addition postulate? Well, like I said, you did it without even thinking about it. You just assumed that the sum of all these partitions represented the entire number of games played. Every single partition is a game. And we have also grouped the partitions so that we have 2 partitions, one of length 6 and one of length 5. We also have 11 total partitions. So you can see that the segment addition postulate is really something that should be very easy for you to remember if you just remember what it really means and don't think of it as a big advanced abstract mathematical concept. It just means that most of the time things add up to the sum of their parts. Like I said before, you can't do that with your dog, but with mathematics you can do it.